Welcome back to G Fun Facts Online, your go-to source for the most exciting developments in science and technology. Today, we're diving deep into a revolution brewing in the skies, a shift that promises cleaner air and a whole new way to fly. We're talking about hydrogen power in aviation. For a long time, the aviation sector has been a significant contributor to greenhouse gas emissions. But now, the race is on to decarbonize, and cryogenic liquid hydrogen, or LH2, is emerging as a serious contender to power the next generation of zero-emission aircraft. This isn't science fiction, folks. It's happening right now, and it could completely redefine air travel. So what's so special about liquid hydrogen? Well, hydrogen is the most abundant element in the universe, and when it reacts with oxygen, the main byproduct is just water. That means virtually zero carbon dioxide emissions where it's used. Plus, its energy density by weight is about 3 times that of traditional jet fuel. Less fuel mass for the same energy? That's a huge win in aviation where every kilogram counts. But there's a catch. To be practical for aircraft, hydrogen needs to be stored as a liquid. And that means cooling it down to an incredibly chilly minus 253 degrees Celsius or minus 423 degrees Fahrenheit. At this cryogenic temperature, hydrogen becomes much denser, taking up less space, though still about 4 times the volume of kerosene for the same energy. This single characteristic means we have to completely rethink how we design planes and their fuel systems. Now, engineering these cryogenic hydrogen systems is incredibly complex. It's not just about making a super cold thermos. We're talking about sophisticated cryogenic storage tanks. These tanks have to be lightweight but incredibly strong to hold LH2 at those frigid temperatures and varying pressures during a flight. They use advanced insulation, like vacuum layers and multi-layer insulation, to minimize what's called boil-off. Basically, the hydrogen evaporating due to heat seeping in. Then there's the fuel distribution and delivery. A whole network of specialized pipes, valves, and sensors is needed to safely move the LH2 from the tanks to the engines, whether they're fuel cells or combustion engines. These parts have to work perfectly under extreme temperature changes and pressures. Interestingly, thermal management is a big part of this. The intense cold of LH2 isn't just a challenge, it's an opportunity. Engineers are designing systems where the cryogenic fuel also acts as a coolant for other aircraft systems, like powerful electronics, or even future superconducting parts in electric propulsion systems. As the hydrogen absorbs this heat, it warms up and vaporizes, which is exactly what needs to happen before it can be used. That leads us to vaporization and conditioning. Before the hydrogen can power anything, the liquid has to be precisely turned into a gas and brought to the right temperature and pressure. This usually involves some clever heat exchangers. And, of course, safety systems are absolutely paramount. We're talking robust leak detection, pressure relief valves, and systems to prevent any flammable mixtures from forming. The path to hydrogen-powered flight isn't easy, though. There are some formidable engineering hurdles. Onboard storage is a big one. Even as a liquid, LH2 takes up more space than jet fuel. This means aircraft will need larger fuel tanks, impacting aerodynamics and design. Engineers are looking at all sorts of tank shapes and placements to make it work. Managing that boil-off on long flights is another tricky part. Material science is also pushed to its limits. The materials used have to withstand that extreme cold without becoming brittle. Specialized alloys and composites are key, and scientists also have to consider how hydrogen itself affects materials over time, something called hydrogen embrittlement. The fuel systems themselves are super complex. Developing reliable pumps, valves, and seals that work flawlessly at minus 253 Celsius is a massive task. Some researchers are even working on pump-free systems that use tank pressure to deliver fuel, aiming to reduce weight and potential points of failure. Integrating all this into an aircraft means significant changes to the airframe, affecting weight balance and structure. We might even see entirely new aircraft designs, like blended wing bodies, that are better suited for hydrogen. And it's not just the planes. We'd need a complete overhaul of airport refueling infrastructure, facilities to produce, transport, store, and safely dispense cryogenic liquid hydrogen. Ideally, this would be green hydrogen, made using renewable energy. Finally, rigorous safety standards and new certification processes are non-negotiable. Public trust hinges on an impeccable safety record, so how can cryogenic liquid hydrogen actually power an aircraft? There are two main ways. First, hydrogen fuel cells. These convert hydrogen and oxygen directly into electricity, with only water and heat as byproducts. This electricity then powers electric motors. Fuel cells are highly efficient and produce zero NOx emissions, making them promising for smaller, regional aircraft. The second method is hydrogen combustion. Hydrogen can be burned directly in modified gas turbine engines, much like jet fuel is today. This approach can leverage existing engine designs, but needs changes to handle hydrogen's different combustion properties. While it eliminates CO2, it can still produce nitrogen oxides, or NOx, though hopefully at lower levels. This is often seen as a more scalable solution for larger aircraft in the nearer term. Many see these as complementary technologies. Fuel cells for shorter routes, combustion for longer ones, at least initially. The aerospace world is buzzing with activity. Giants like Airbus, with their Zero program, are aiming to have a hydrogen-powered commercial aircraft by 2035. They've recently highlighted concepts with fuel cell-powered electric engines. Startups like Zero-Aviation are developing hydrogen-electric powertrains for regional aircraft. H2FLY, now part of Joby Aviation, achieved the world's first piloted flight of a liquid hydrogen-powered electric aircraft in 2023. Big names like CFM International, a partnership between GE Aerospace and Safran, and Rolls-Royce, are deep into hydrogen combustion research. And countless universities and research groups are tackling the fundamental challenges. For instance, Florida State University researchers recently designed an innovative liquid hydrogen storage and delivery system that also uses the hydrogen as a coolant. Projects like CHEETA in the US and Clean Aviation in Europe are fostering vital collaboration. The Overleaf project in the EU is focusing specifically on advancing liquid hydrogen storage tank technology. It's a tough field, though. We saw Universal Hydrogen, which was working on modular hydrogen solutions, cease operations in mid-2024 despite successful test flights. It just underscores the huge financial and technical hurdles, but innovation is marching on. We're seeing advanced tank designs using lightweight composites and better insulation. There is work on active cooling systems and ways to reuse boil-off gas. Some are even exploring hyperconducting systems, using the extreme cold of LH2 to supercool electrical components, making electric propulsion much more efficient. Integrated systems that combine fuel storage, delivery, and thermal management are also emerging. And of course, continuous improvements in fuel cell power density and advanced hydrogen combustion techniques are making these technologies more viable. So what does the future hold? The journey to widespread cryogenic hydrogen aviation is a marathon. Beyond the tech, we need a massive scale-up of green hydrogen production. Airports worldwide will need new infrastructure for LH2, a colossal investment. New regulations and certification standards have to be developed. The economics have to make sense. And, critically, it will require unprecedented collaboration across the entire industry. Despite these hurdles, the momentum is undeniable. Cryogenic hydrogen systems are a cornerstone of aviation's dream of a zero-emission future. The engineering brilliance being poured into this field is paving the way for aircraft that will not only carry us across the globe, but also carry the promise of a cleaner planet. We'll likely see these technologies appear first on regional aircraft, then gradually expand. The goal of having the first hydrogen commercial aircraft in service by 2035 is a powerful driver for all this intensive research. It's an exciting time, and we're looking at a future where the only thing our planes leave behind is water vapor. That's all for this episode of Fun Facts Online. Join us next time as we explore more amazing breakthroughs shaping our world.